Hello everyone, we will continue with the equivalent circuit model of the induction motor. So, you know the equivalent circuit on the screen. We have the transformer equivalent circuit and we will make some modifications to obtain the induction motor equivalent circuit. So, let's start with the short circuit cable of the output side. If you remember, in the rotor part, we have short circuit rings through the rotor conductors. So because of this, we will add a short circuit cable to the output side, because we will not get the electrical energy from the output. We will take mechanical energy through the R2 resistance. So what else? In the previous topic, in the transformer, our conversion through the ideal part was A, the turn ratio. But in here, as we discussed previously, the slip will be the conversion ratio. So if we have the induced voltage of E1 here, we can say in that part we have S times E1. The slip will be active through the conversion part, through the air gap. What else? The frequency. So our applied frequency, applied voltage frequency is Fs, but in the rotor part we have Fr, which is S times Fs. So that means all the frequency related parameters must change. For example, the X, the reactance, it is the ohmic value of the inductance. So according to previous value, we have to add the slip to here, because the generally X is equal to 2 pi f L. So if our frequency will change, the reactance value must change. So what we have finally, R1, X1, RC, and XM for the stator part components, and X2 and R2 for the rotor part of the induction motor. And also we discuss in the transformer topic, we can simplify by eliminating the conversion part. We can integrate the conversion inside the parameters and we can use a single circuit. How we will do this? Let's try to simplify by using the current relation. For example, the current flowing through here, if I2 can be written from the rotor side Kirchhoff's voltage law equation, S times E1, the total input voltage of the rotor side, divided by total impedance. What is the total impedance? R2 and J as X2. So let's simplify this expression by dividing to S, to numerator and the denominator. So E1 over R2 over S, J X2 will be the equation. So what can we say? We can eliminate that part from the figure and we can write our SE1 according to which is referred to E1 if we change our impedance like this. So let's try to draw. That means we need to start with our stator components, which are R1, X1, RC, and XM will remain. And we will eliminate the conversion part. We will use our secondary side, rotor side components directly here. We have only two components. The first one, according to here, must be Jx2, and the second one must be R2 over S. S represents the slip in the equivalent circuit. So this is the full equivalent circuit of the induction motor, and this is the per phase equivalent circuit. So we have phase to neutral voltage and phase current. They will be the input part of the equivalent circuit. What about the parameters? Actually, we are familiar with the parameters. In the stator and the rotor part, we have, first of all, R1 and R2, which represents the stator winding resistance and rotor winding, or according to rotor type, conductor resistance for R2. X1 and X2, they represent the leakage reactance, leakage flux reactance for the primary, for the stator, and the rotor part, for the secondary part. RC represents the core losses, which are the, again, hysteresis and eddy current losses. And because of their phase difference with respect to applied voltage, they are in phase, their effect in the circuit will be in phase. Because of this, we represent it by a resistance. And another one, XM, which represents the magnetizing reactance, similar with the transformer, to be able to induce a voltage on the rotor side. On the secondary side of the system, we have to supply the IM magnetizing current, which is flowing through the magnetizing reactance. Okay, so until X2 parameter, we have the stator parameters. After that, we will skip the air gap and we will reach the rotor parameters of R2 over S and X2. And let's make some simplifications for the equivalent circuit. So this is the general version for the induction motors, but in the industry we have many different applications for the induction motors. Because of this, according to our calculations, according to our focus on the system, we can make some simplifications or some modifications in the equivalent circuit to calculate our parameters easily. For example, the approximate equivalent circuit. For the approximate equivalent circuit, what was the criteria? We have an excitation branch here with the components of RC and XM. And according to our experimental studies, we know RC and XM are very big in terms of their values. And that means the current flowing through that part must be very small when we compare with the main current of the circuit. So we can slide the excitation branch to another part of the circuit. Why? Because when we examine this general equivalent circuit, we have first of all series connection to calculate the total impedance of the circuit, then a parallel connection, then one more series part we have. So instead of this, if we slide the excitation branch to the beginning of the circuit, the parameter values will not change because we are not changing the voltage level. The remaining parameters will be connected in series. So that means, first of all, we have a series connection, then parallel. We can eliminate one calculation of the general equivalent circuit of the induction motor. And the parameters of the circuit will be protected. They will not change. And again, we have V1 and I1. These are the phase voltage and the phase current. As I said, this is the per phase equivalent circuit representation. And for this part, we are talking about three-phase systems. So that means according to your connection type, you must connect your phase and neutral points to correctly to create your three-phase connection. And this is the approximate equivalent circuit. What else? For the experimental studies, simplified equivalent circuit of the induction motor also preferred. For example, we can use R1 and X1 first of all. Then for the rotor, again we have X2 and R2 over S. But in the middle part, instead of a parallel connection of RC and XM, we have only the XM parameter. Why? This circuit is mostly used for the determination of equivalent circuit parameters. So in that case, it's very hard to determine the value of RC. Its value is combined with the rotational losses of the induction motor. So its effect still protected, but in terms of the equivalent circuit model, we cannot use specifically. So this is the simplified equivalent circuit. And we have one more model for the equivalent circuit of the induction motors. It will be the modified equivalent circuit. Why? To clarify all the losses and the powers, to make a connection between the power flow diagram and the equivalent circuit, we have this model. How the model is look like? Let's continue with the modified equivalent circuit. So it is actually very similar with the first one. R1, X1, and the excitation branch will remain with RC and XM. And then X2 will come, but we will use two resistances instead of one. What are they? R2 and R2 1 minus S over S. So if you add these two resistances, still you have R2 over S. So we didn't change anything, only we separate into two parts. We divide into two parts our R2 over S. Why? To clarify the losses. For example, if we start with the first resistance of the equivalent circuit, R1, what was the R1? Which represents the stator winding resistance. So if we can calculate the absorbed power by the R1, we can determine the stator copper losses. Similarly, the next resistance in the circuit will be the core losses. So, according to RC, if we can calculate the power absorbed by the RC, we can determine the value of core losses. The next resistance, R2, which is similar with R1, it represents the rotor conductor winding resistance. So because of this, rotor copper losses can be calculated through the R2. And the last resistance, it is not a loss, it is the converted power. So after all the electrical losses, this amount of power will be transferred to the mechanical conversion. And if we subtract the rotational losses, we can obtain the output power. Okay, so let's make a connection between this modified equivalent circuit and the power flow diagram of the induction motor. So when we examine the power flow diagrams of any motor or generator, we are using the Sankey diagram representation. So we are using arrows, and the width of the arrows shows the amount of the power flowing through that point. So for the power flow diagram, we will start from the input power, and until to output power, we will subtract the losses from the system, and we will clarify the power relation between the parts. So let's start with the input power. So we have three-phase system. We can use two different expressions to clarify, to write an expression for input power. The first one can be the simple one, I think. V phase, I phase, and cosine theta can be multiplied by 3. So if you know the phase voltage and phase currents and the power factor, you can multiply by 3. Or if we know the terminal voltage and the line current, in that case, square root 3 V terminal, IL, and cosine theta also can be used. So this is the input power. According to specifications of the machine, this amount of power will be applied to the system, applied to the motor. Then we should continue with the losses. According to our modified equivalent circuit, the first loss in the system will be the stator copper losses. So from here, we will take the stator copper losses out. And how can we calculate the stator copper losses? Let's see the circuit. So we have a three-phase system. So because of this, we must use R3. Then I square R expression can be used because mostly we know the current flowing through this resistance. So the current flowing through the stator copper losses resistance, stator winding resistance represented R1, I1 square times R1 will be the expression. Then the next resistance in the equivalent circuit is RC. So that means from here we have less power, but we can use the core losses. We can take it out. And how can we determine the core losses expression? It is connected to circuit in parallel, and according to our experience, we know the induced voltage on this resistance. So if the voltage on the RC is E1, you can use 3 times E1 square over RC to calculate the core losses. After that, before the next loss, we have a critical point because we will transfer the power, remained power in the stator to the rotor. Through what? Through air gap. So the total power, remaining power at this point can be called as air gap power. For air gap power, we can use the power flow diagram relation, and we can say input power minus stator copper losses minus core losses. Or we can use the transferred power to the rotor from the equivalent circuit. So 3 times the current flowing through the right side, if I2 square times the total resistance on the secondary side, R2 over S. Then we can continue to the rotor part, and we can take out the first loss of the rotor side. What is it? Which is represented by R2, rotor copper losses. So rotor copper losses will be the next loss of the system. How can we calculate? For the rotor copper losses, it will be similar with the stator copper losses. So 3 times the current flowing through the rotor copper resistance, R2. Then we have the converted power. So for converted power will be another point similar with the air gap. So it can be shown like this. And for converted power, we can write an expression from the power flow diagram. It will be air gap power minus rotor copper losses. Or, again, through the equivalent circuit, we can write 3 times the current flowing through that part times the resistance, which represents the converted power. That means 1 minus S over S. This resistance R2, 1 minus S over S, is the representative of the converted power. So when we compare these two expressions, what we have? We can write converted power is equal to 1 minus S air gap power. So we can obtain also this expression. What's the next one? After that, we finished all the electrical losses in the system, and converted power will be the mechanical input power of the induction motor inside. So because of this, in here we have the mechanical losses. These are friction and windage losses. And the next one will be the stray losses, and it is generally defined as the undetermined losses of the system during the construction because of the tolerances of the materials or the conductors. And finally, we can find the output power. Friction, windage, and stray losses, they are totally will give us the rotational losses of the system. And additionally, stray losses are determined as 1% of the input power generally because it's not possible to calculate its value. But if we want to consider the effect of the stray losses, we can take as 1% of the input power. Okay, so let's continue with the output power equation from the power flow diagram. The last power we have calculated is converted power. So through the converted power, if we continue from the losses, we have output power converted minus friction, windage, and stray losses. And in addition to that, we have for the output power a mechanical power output. So because of this, we can write load torque and Wm. And similarly, for the converted power, we can write a mechanical expression. Why? Output power is the mechanical output power value of the system. But after the electrical conversion to mechanical, we have the converted power input to the mechanical side of the induction motor. So because of this, the equation can be induced torque times Wm for this point. Related to rotational speed, we can say the air gap left side has Ws. If we want to calculate any parameters related to speed, we should use the Ws, but after air gap, our speed for each calculation must be Wm. Okay, thank you for watching.